Notice my Gatorade here. Thirsty all the time. Anyway, so this video we're going to just talk about what a complete graph is. It's a type of connected graph. It's the type of graph that we're going to be talking about when we talk about traveling salesperson problems. So a complete graph is a graph where you have every vertex has an edge going from it to every other vertex in the graph. So I'm going to draw a complete graph that has 4 vertices. So we have an edge going from that vertex to that vertex, this vertex to that vertex, this vertex to that vertex. Let me label these. So this vertex has an edge going to that vertex, this vertex, and that vertex. This edge has, or this vertex has an edge going to that vertex, and this vertex. Now D already has an edge going from it to every other vertex. So that's a complete graph. Every vertex has an edge going from it to every other vertex. Notice when you have a complete graph like this, you're always going to have a Hamilton circuit in the graph. Okay? And if you have a Hamilton circuit, you're also going to have Hamilton paths. So all these graphs are going to have Hamilton circuits and Hamilton paths. When you have 4 vertices, this is called K4. Okay? That's how you label complete graphs or describe complete graphs. It's K and then N, where N is the number of vertices in the graph. Okay. So that's a drawing of K4. I'm going to draw a K5. Once you get to a certain number, they're really hard to draw. So I probably won't do K6, but I suppose I could. So that's K5. Every vertex has an edge going from it to every other vertex. You can see that, yeah, when you get higher numbers, it'll be really hard to draw. I think I've actually drawn up to, on my own, like, on a piece of paper. I think I drew K10 where it looked kind of all right. I don't want to say it looked good, but it looked all right. Alright, so I think in this video I also talk about the beginning of a traveling salesperson problem. So, traveling salesperson problem has to do with, I'm going to go back to drawing K4. Okay, so this is K4. Now, think of each vertex as a city or a town, or it doesn't matter, but just a different location. And there's maybe mileage in between all the cities. Traveling salesperson wants to minimize how much he has to travel. So there's different circuits, Hamilton circuits in this graph. He wants to make sure he picks the one that has the least mileage. Okay, I'm not going to label all the edges with their mileage right now. I'm just giving you an idea of what the problems are going to be like. In the next video, I'll talk about the brute force algorithm, which is one of the ways, it's the only real way to actually figure out the best route. But for right now, I'm going to just talk about how many different ways you could do this. Okay, well, it turns out that if you have kn, there are n minus 1 factorial Hamilton circuits. Remember, we want circuits because if you're a traveling salesperson, you're going to start in a city like where your headquarters are or whatever. Maybe you have to go from Cortland to Buffalo, then to Buffalo to Binghamton, Binghamton to Albany. But then eventually you're going to come back to Cortland. So it's a circuit. You're finishing the same place you start. So we're interested in how many Hamilton circuits there are. Okay, so K4, well, for Kn there's n minus 1 factorial Hamilton circuit. So for K4 that would mean that there are 3 factorial, which is 6. There's 6 different ways you could make a Hamilton circuit with this graph. And I think I'm going to write them down right now. So let's say we're starting at A is where our headquarters are. So I could go from A to B to C to D and back to A. That's one Hamilton circuit. Okay. I could go from A to B, then B to D, then to C, then to A. Okay. Then I could go from A to C to B to D to A. I could go A to C to D to B to A. Then I could go A to D to B to C to A. And lastly, I could go from A to D to C to D to A. Those are the 6 ways. I don't know why I got shorter as I went down, but notice I did it in a pattern, right? I said, it makes sense to go from A to B. Like I used the alphabet to do it. And then C, D, A. Well, I realized I could also go from A to B, and then instead of going to C next, I could go to D next. These are the only 2 ways you could do it, where you start at A and then go to B. Then I decided to start it where I went from A to C, and these are the only 2 ways you could do it that way. If you can think of another way to do it, let me know. There's no other way to do it. So, the brute force algorithm, which I'm going to talk about in the next video, has to do with you figuring out the mileage, or whatever you're talking about. It doesn't have to be mileage. It could be like how much it costs to go from A to B. But usually we're going to be talking about mileage, I guess. They'll let you know in the problems. I'll let you know in the problems too, if I make up the problems. So the only way you can actually figure out the best route is to actually calculate how many miles every route is, or whatever you're talking about. Okay? Well, the problem with the brute force algorithm is going to be, and I'm going to talk about that in the next video too, is that if this n gets really big, they talk about this in the book, and I think that it's really interesting. If K was, not K, if N was 30, what would happen? Well, obviously you'd have 30 different vertices, but what does that mean? Well, it'd be a lot bigger, right? Well, how many of these would you have over here? Well, you'd have 29 factorial, because remember it's n minus 1 factorial. So that would be 30 minus 1, which is 29 factorial. 29 factorial is a big number. I don't have my calculator out. I do have it with me, but I don't want to put that in my calculator anyway. So they talk about in the book that if you were to write out all these for K30 and then calculate the best route, if you had the world's fastest supercomputer, you might be thinking, well, gee, the world's fastest supercomputer could probably do it just like that. So it might take me a long time to do it by hand, but the world's fastest supercomputer could do it like that. I mean, it's the world's fastest supercomputer. But it turns out that even for K30, the world's fastest supercomputer, it would take 280 million years to figure out the best route. And they go on in the book to say that in real life, some of these problems that companies have to do have K 50 to 100. So basically, for K100, the world's fastest supercomputer, it would take the amount of time that's already existed in the world would not have been enough. So right at the beginning of time, if the computer started trying to figure out the best route for K100, it would still not have figured it out. It wouldn't be anywhere close to figuring it out. So the brute force algorithm, which I'm going to talk about in the next video, is not a great way to figure out. It's the only way to figure out the exact best route, but it's not a good way to try to figure out a good route quickly because it takes too long. So in the next video, we're going to talk about the brute force algorithm.